Hey, welcome to class number 3. I think we're going to try to do this one in one lecture, so only one video. And the class is going to be about minerals. And so far we've been talking mostly about igneous rocks and how those rocks are formed from the original starting materials of the solar system and the mantle. Now we're going to switch gears a little bit and look at the minerals that actually make up those rocks. And minerals are important. For one thing, they record these processes we've been talking about. A lot of what we know about these processes is from analyzing microscopic aspects of minerals that actually record some of these environmental changes. And of course, minerals are super important to society. Pure mineral ore is the source of almost every industrial material. And I've motivated that a little bit with this photo of brine pools. These are liquid brines in the Atacama Desert in Chile. What they're doing here is they're actually evaporating off the water and crystallizing out lithium-based minerals. And these lithium-based minerals are then going to go on to be used in batteries in your cell phone, in your hybrid car, everywhere. So all those things you own all start as natural minerals. And of course, minerals are also an inspiration for materials science. A lot of the new materials that are developed in labs are based off existing mineral structures. So it makes sense to know something about those natural mineral structures before you can understand something synthetic. So what will we learn in this video? We'll first learn about silicate versus non-silicate minerals. Then we'll talk about chemical bonding and the silica tetrahedra. We'll talk about silicate minerals, which are the most common minerals on Earth. Then we'll look at Bowen's reaction series, which predicts which of these minerals should occur in a given igneous rock. And then we'll look at fractional crystallization and talk about how that can give us different igneous rock types from the same melt. So building on that motivation, I've included this figure that shows the world's reserves of lithium. You can see they're not in every country, only certain countries have lithium. Most of them are centered here in Bolivia and Chile, up in the high Andes. And I've also put in this very up-to-date cost summary, which shows that really in the last few months, the price of the mineral, lithium carbonate, that's a mineral, has basically tripled. So it would probably be pretty handy to understand what the world's reserves of this mineral look like, and also maybe what some alternative minerals are that might replace lithium carbonate. So a quick review, what are minerals? They're crystalline solids that form in the natural environment. They have a repeating crystal structure and they have a constant composition throughout. What should you be picturing when you think of minerals? Well, you might be picturing something you saw in a museum case in By Hall or in the Natural History Museum. And of course, these are all individual minerals. They all have their same crystal structures and a constant composition. But they're also gems. They're these beautiful examples of minerals. Minerals also make up all rocks on Earth. So we can also think of them in this really bulk scale, where you might take a backhoe and go strip mine a hillside somewhere and try to process out minerals in large quantities from a lot of initial bulk rock. Now there's two important groups of minerals. These are the silicate minerals and the non-silicate minerals. And the difference is that silicate minerals have silica and oxygen as the fundamental building block of their crystal structure, whereas non-silicate minerals can come in a variety of different forms. We're not going to talk much about non-silicate minerals in this class, but it's worth showing a list of some common non-silicates: carbonates, oxides, sulfides, sulfates, and then some elements that actually just occur in their native form, like gold. So common oxides include magnetite and hematite. These are iron ore. Of course, calcite and dolomite are carbonates, and those are going to make up most limestones. They're going to make up a whole class of rocks that we're going to see later. Here's a halide, sodium chloride, that's common table salt. So you may already be familiar with a bunch of these minerals. So a quick review from last class. First, remember that all rocks are ultimately derived from mantle peridotite, and it's partial melting that helps to enrich the silica and aluminum out of that peridotite into crustal rocks. And all of this is driven by tectonics. It's creating partial melting at mid-ocean ridges and also at subduction zones. So in the last class we talked a lot about partial melting, how we take a source rock, we melt some of the minerals in it, we get a magma, and then we cool that magma to make a new igneous rock. So today we're going to pick up on this cooling process, this fractional crystallization it's called. And we're going to show how we can start with the magma of a given composition, crystallize a bunch of different minerals out of it, and actually even create multiple types of igneous rocks from the same magma. So again, let's think about the setting. Fractional crystallization is going to happen in a magma chamber. So you might picture the magma chamber below the mid-ocean ridge that we've already mentioned a couple times. In this magma chamber, it's literally a pool of atoms, silica, oxygen, sodium, calcium, that are vibrating around, and initially they're really too hot to bond. There's too much thermal energy vibrating and preventing bonds from forming. But eventually those atoms are going to start to share electrons. They're going to start to bond, either ionically or covalently, and they're going to start to assemble themselves into mineral structures by bonding. And what determines the types of bonds that can form is called electronegativity. And this is a basic chemistry concept you're welcome to review online, but we'll hit it quickly here. This is the idea that each atom can be characterized either as a positive cation or a negative anion. Okay? And what that means, if you're a cation, it means you want to give away electrons, or you'd like to share generously of the electrons you have. If you're an anion, it means you'd like to receive electrons, or like to borrow another atom's electrons. And this is determined, of course, by the orbital structure. Electrons exist in orbits outside of the nucleus, and you might remember that often these orbitals want to be full. Well, they always want to be full, often with 8 electrons in the outer shell. So whatever number of electrons gives a full shell, if you have additional electrons that exist in that next shell that's not full, it's easiest to give those away, especially if you just have 1 or 2 extras. You may want to give those away, and that's going to make you a cation. Like potassium here is a +1 cation because it has this 1 electron in its outer shell, doesn't really fit well, and it wants to give it away. Other elements, if you had, say, for example, only 7 electrons in this shell, you might want to get an extra electron that would complete this shell, and that would make you an anion. This is a great summary diagram of cations versus anions. What it shows is the chemical abbreviation followed by some dots. And the dots represent the number of electrons in that outer orbital shell. So lithium, for example, has 1 electron in its outer orbital shell. It would love to give that away or share it. That makes it a +1 cation. Magnesium has 2 electrons in its outer shell. That makes it a +2 cation. Let's flip to the other side here. Chlorine has 7 out of 8 electrons in its outer shell. It would love to fill that 8th spot, so it's a -1 anion. So you get the idea. Anions are going to want to pair up with cations to exchange or share electrons, so everybody has a mostly full outer shell. What about the middle here? I call these the switch hitters. Carbon, silica, germanium. These are really important elements because they're equally happy to give away 4 electrons or to receive 4 electrons. their outer orbital shells are half full. So it doesn't matter to them if they give 4 away or they receive 4. And that makes them incredibly versatile in how they can interact with other elements. So it's no coincidence that carbon is the basis for all life on Earth, humans, trees, plants, where silica is the basis for basically all rocks on Earth. So these are really important elements. And here's how silica is important in rocks. All silicate minerals are based on the building block called the silica tetrahedra. What that is, it's a silica atom plus 4 surrounded and bonded to 4 oxygen atoms, which are -2 anions. So these are covalently bonded and they're sharing electrons, trying to neutralize each other's electronegative charge. But if you add up the sum of all these charges, they don't add to 0. They're not neutralized. The silica is +4. The oxygens are a total of -8. That means this tetrahedra has a net charge of -4 across it. So it's not really stable. It's still looking for more cations to balance out that charge. So that's exactly what happens when we make minerals. We bring in additional cations, like magnesium, arrange those magnesium ions between the tetrahedra, and balance out the charge, and in the process we make a mineral, like olivine. So olivine is really the simplest silicate mineral. It's a bunch of silicate tetrahedra, those are represented by this yellow figure, with magnesium and iron literally interspersed between those to try to neutralize the charge. Now, it's no coincidence that we use magnesium and iron to neutralize the charge. If you look back a couple slides, you'll see that magnesium's a good +2, and iron's not on here. Iron can either be a +2 or a +3 cation. So they're really efficient at balancing the charge. And a key point here is that as silicate minerals grow in a magma, they look to incorporate the stronger +2 cations first, because those cations are better at neutralizing the charge. But eventually, we can't neutralize all the charge with magnesium and iron. So what starts to happen is the silica tetrahedra start to share oxygens. And they start to share oxygens at the corners. What that means is that each time there's a sharing, it means there's one less oxygen atom involved, which means there's a little bit less negative charge. And it's easier to balance the charge across this more complicated structure. And here we go. Now we're building silicate minerals. We went from an isolated silicate structure. This is now called a single chain structure as we've started to join the oxygens. An example of a single chain silicate is pyroxene, which is common in basalt and other igneous rocks. So as the magma continues to cool, we get more and more sharing of oxygens between the tetrahedra. In this example of a sheet silicate, you can see that each tetrahedra is sharing 2 oxygens. So three. 3 of the corners are being shared. So now we've eliminated a bunch more oxygen, which means less negative charge. And what that means is that it's much easier to neutralize that charge. We can do it with weaker +1 cations, say potassium or sodium. And so now it's okay to start bringing those +1 cations in. And sometimes we can think of this as they're being forced to use those. There were no more +2 cations available to neutralize the charge. So we're forcing these tetrahedra to start sharing oxygens and using the +1s. So not only are we bringing in different unique +1 cations, we're also enriching the mineral structures in silica. Because we're using less oxygen per silica, the overall percent silica is going up. So these are felsic minerals. They're minerals that have more silica in them. And they also tend to have more potassium, sodium, and aluminum. And the reason they'd have that is because they're making these more complex structures. So just to be formal, this is a sheet silicate structure, and then we've got a framework silicate structure. So the sheet silicates are commonly micas, like biotite or muscovite. Literally, they flake apart in sheets. Framework silicates include quartz and feldspar, which of course are really common ingredients in granites and felsic rocks. Now that you know something about the crystal structures themselves, let's step back and look at how this plays out as a magma starts to cool. Okay? When do these different minerals crystallize, and what controls that order of crystallization? Well, this is predicted by a concept called Bowen's reaction series, and it's summarized here in this chart. Okay? You can think of this as a magma cooling from high temperature at 1200 down to low temperature at 750. And what we're going to see here is, in these different colored bars, different minerals starting to crystallize. Along the left, we're going to see what's called the discontinuous series. Along the right, we're going to see what's called the continuous series. This involves mostly plagioclase feldspar. This involves olivine, pyroxene, amphibole, and biotite mica. And over here, you'll see generally what kind of rock type you'd make if you were crystallizing out minerals in this range. So as we described, the first silicates to form are the simple silicates. For example, olivine, that isolated tetrahedra structure where there was no oxygen sharing. And again, they're going to grab up those +2 cations because they need them to neutralize the charge. Same with pyroxene, it was that single chain silicate. So what's happening? As these minerals crystallize, they're soaking up all the iron and magnesium, and also calcium. So we tend to think of those as mafic elements, and these are mafic minerals. Now once they're crystallized, those elements aren't available in the melt anymore. If we want to make additional minerals, we can't make them with magnesium and iron because there's not much of that left. So what do? We start to force the sharing of more oxygens. We start to build more complex silicate structures. And a lot of these are going to incorporate the +1 cations, like potassium or like sodium-rich feldspar. And of course, when we crystallize out these minerals, because they're sharing oxygens, they have more silica, a higher percent silica, which makes them felsic. Okay? So a final point is that crystallization is temperature dependent. These simpler silicates, the mafic silicate minerals, tend to crystallize at a higher temperature, and these more complicated silicates, the felsic silicates, crystallize at lower temperatures. So imagine you have a high temperature magma that doesn't have any magnesium or iron in it. You can actually cool that magma way down, and you're not going to have any crystallization because all these minerals need magnesium and iron or calcium in order to crystallize. But if you don't have any of those mafic elements, then you're just going to keep cooling down into a temperature range where you can finally start to crystallize some minerals that involve elements that you have, potassium, for example. And a final point is that, of course, as you're cooling through these temperature ranges, if you don't have any of the ingredients, you can't make the mineral, and nothing crystallizes. Okay? So if you don't crystallize any of these mafic minerals, then you're going to be left with a felsic rock once that magma is cooled. So let's just quickly sum this up on our old friend, the igneous rock diagram. We might end up with a mafic rock like a basalt if the melt is rich in iron, magnesium, and calcium. And that's going to be made of simpler silicate minerals like plagioclase, pyroxene, and olivine. But if we didn't have any iron, magnesium, calcium, we'll be left with something more like a felsic rock. It might be rich in silica, sodium, and potassium. And we can see that down here. We know that as our silica content increases towards felsic, that's because all these minerals are sharing more oxygens and they're enriching their relative silica concentration. Likewise, they're able to incorporate those +1 cations, potassium and sodium. But mafic rocks, of course, are incorporating more iron, magnesium, and calcium, more of the +2 cations. And then again down here we see that you can start to crystallize a mafic rock at 1200, and you might not crystallize a felsic rock until 700 or 800. It's worth noting that crystallization and melting happen at the same temperature, so those would be the same numbers along this axis. So I'd like to finish the lecture by stepping back at the scale of the magma chamber again and looking at how the sequential crystallization of these minerals is actually changing the composition of the remaining melt, and it can actually end up giving us igneous rocks of very different compositions that can actually crystallize from the same melt. And this idea is called fractional crystallization. And the core of the idea is that once elements, like iron and magnesium, are incorporated into a mineral, like pyroxene, those elements aren't available anymore. They're locked up in that crystal structure, and so any minerals that want to form later can't use those elements. They're gone. And what does that mean? Let's take a look at it in this cartoon. So we start out with this magma chamber that has all the elements available. And then according to Bowen's reaction series, let's say we start to crystallize pyroxene first. Up at a higher temperature, we start to use up those +2 cations, like magnesium and calcium. Okay? Those crystals are no longer interacting with the melt. They might sink to the bottom of the magma chamber, for example, and you can see that we have a lot less melt now. And the melt that's remaining, of course, is now enriched in +1 cations. So now, according to Bowen's reaction series, we're forced to start making these more complicated silicate minerals that are going to start sharing oxygens, and they can utilize the remaining +1 cations, maybe like potassium or sodium. And the result is that we crystallize more complicated silicate structures, maybe potassium feldspar or sodium plagioclase. And those crystals might settle out later. And of course, they're going to give a rock of completely different composition than the rock in which was formed first by the mafic minerals settling out. So the process of fractional crystallization has actually given us two different rock types from the same magma chamber. So here's an example of what that might look like. This is a rock you might find at the bottom of a magma chamber. We've got a mafic gabbro filled with some pyroxene, maybe some biotite, and then on top of it we've got a granite, which has quartz and feldspar and is generally much more enriched in silica. In closing, I just want to step way out now and remind you, what do these magma chambers look like in the natural environment? Here's another one. This is the famous towers at Torre del Pan in Patagonia, Chile. Please excuse my awful Spanish. What you're seeing here is the cooled granites of a magma chamber, and capping this granite is actually a metamorphic rock that was actually heated and cooked as the granites pushed their way in under it. So literally you're seeing the contact here between the magma chamber and the rocks that were already there to begin with. And of course this strong granite is eroding into these steep cliffs, making fantastic mountaineering and rock climbing. So here's a summary of all the concepts related to both partial melting and fractional crystallization. You're welcome to look at it in the PDF printout of the slides. I won't go through them now. Here's the concept questions from this class. Please take a minute and familiarize yourself with them and look back over the slides. And then go ahead and take this quick one-question quiz online. You'll need to copy this link into your web browser. And that's it for class number 3. We'll see you in a couple days for class number 4, where we'll look more in depth at subduction zones. Thanks.